Lithium-ion batteries are the preferred technology for portable electronics, automotive application, and stationary energy storage. By 2030, the dual green and digital transition will drive an exponential increase in the production of these batteries, consequently require large quantities of raw materials for their manufacturing. The European Union, through various community initiatives, aim to play a key role in lithium-ion battery production, challenging Asia's dominance in the sector. In this lesson, the European Union legal frameworks and the approach developed for end-of-life battery recycling will be described as possible source of secondary raw materials for battery manufacturing in Europe. Production of lithium-ion batteries requires several critical raw materials. Critical raw materials are materials with significant economic importance to Europe, but characterized by a high supply risk as they come from non-Europe countries that hold a monopoly or are subject to political instability. In addition to this, there are strategic raw materials which are essential for the energy and military sectors and are expected to see increased demand in the future. Since 2023, all strategic raw materials are also classified as critical raw materials. The critical raw materials necessary for lithium-ion battery production include cobalt, lithium, manganese, graphite, phosphorus, aluminium, while the strategic ones include nickel and copper. The availability of this raw material is crucial for developing the European battery manufacturing sector and reducing dependence on Asian producers. Despite the lack of known deposits and dedicated mining activities within Europe, the European Union is actively promoting independence in raw material supply. This includes reopening mines and streamlining administrative processes in accordance with the Critical Raw Materials Act. The goal is that by 2030, the European Union should extract at least 10% of its critical raw materials needs, process 40%, recycle 15%, and import less than 65% of any critical raw material, ensuring that no more than 10% comes from a single non-Europe country. Recycling end-of-life lithium-ion batteries is a key strategy for securing the critical raw materials required for their production. This is in line with the new Battery Regulation 2023, which provides for minimum percentage of recycled material for the production of batteries placed on the European market starting from 2030. However, their complex structure, chemical composition variability, and the presence of flammable solvents pose significant challenges to large-scale recycling process. Recycling processes can be categorized into different types: pyrometallurgical recycling, hydrometallurgical recycling, and direct recycling. The simplest traditional approach includes pyrometallurgical processes with direct feed of the whole batteries into furnaces without prior physical treatments. This method has a low recycling efficiency. In fact, it recovers only the most valuable metals, while consuming large amounts of energy and generating environmental impacts. The resulting alloys require additional processing to be reused as secondary raw materials for cathode material production. As downsides, graphite is not recovered and lithium is lost in the slag. Hydrometallurgical processes are a more sustainable approach that enables the integral recovery of raw materials. The process is applied to black mass, a mixture of anode and cathode material obtained after battery disassembly and metal scrap separation. The recovery process involves dissolving metal oxide and extracting graphite as a solid residue, which after further treatments can be used to produce new anodes. The solution containing all metals, called leachate, is treated to separate the metals and recover them as salts, which are reused for cathode production. The main advantage is the higher recovery rates compared to pyrometallurgy. Finally, there is the most advanced approach, Direct recycling regenerates the structure of the black mass without melting or dissolving it. This method has major economic advantages as it reduces the number of processing steps. However, significant technological challenges remain as direct recycling requires highly efficient pretreatment to obtain impurity-free black mass, needs separation of anode and cathode components, and must include automated sorting methods to ensure that only batteries with homogeneous chemical composition enter the process, guaranteeing product quality and process efficiency. Recycling processes can be compared from different points of view. The economic sustainability of recycling method is evaluated based on investment and operational cost versus revenue from recovered materials. Direct recycling has the lowest processing costs and the highest potential revenues as it produces high-value cathode materials with minimal steps. However, the technology readiness level of operation required in direct recycling is still low, requiring further developments. Considering environmental impacts in terms of energy consumption, pollution emissions, and the environmental credits from resource recovery, pyrometallurgical processes present various disadvantages that are difficult to overcome. Hydrometallurgical processes are the best compromise for industrial scale application, offering low environmental impact due to lower energy consumption and high recovery rates. Nevertheless, the structural complexity and chemical variability of end-of-life batteries requires further technological advancements, specialized expertise, and pilot-scale projects to assess the technical and economic feasibility of the developed processes. Within this complex framework, the research group on theory of chemical process development at the Department of Chemistry, Sapienza University of Rome, is currently engaged in activities related to the technological transfer of a recycling process involving the resynthesis of electrode materials. Among the various hydrometallurgical strategies, recycling with resynthesis represents a particularly innovative approach. Instead of separating metals from the leachate, this process directly produces mixed NMC cathode precursors through coprecipitation, followed by thermal treatment with a lithium compound. Lithium remaining in solution can be recovered as lithium carbonate. The benefit is integrating end-of-life battery treatment with the production of anode and cathode materials, reducing investments and operational costs while minimizing process steps. In particular, within the PNRR CN4 Spoke 13 Task 3.3, research is focused on transition from batch production to continuous production of cathode precursors. This process uses oxalate as precipitating agent. Compared to classical production method, which involves the coprecipitation of hydroxide, this approach offers several advantages. The shift to continuous production represents a fundamental step in scaling up the recycling and resynthesis process to high capacities. In conclusion, the rising need for lithium-ion batteries calls for smarter and greener ways to recover the essential materials they contain. Innovative recycling methods, like the one being developed at Sapienza, can help Europe reduce its reliance on imports, support local production, and contribute to a more sustainable future in line with the green transition.